What if I told you that there's one single piece of technology that's so fundamental it powers almost everything? We're talking about the plane you fly in, all the way down to the light bulb in your room. It really is an engine hiding in plain sight. And I think it's about time we figured out what it really is. You've definitely seen this before, right? It's the heart of a modern jet engine. And the whole point of this amazing device, which is called a turbomachine, is to move energy around using a fluid. In this case, that fluid is just air. So those compressor blades up front, they cram energy into the air. And the turbine blades at the back, they pull energy right back out of it. That little dance, that interaction, that's the core secret that not only makes a jet fly, but as you're about to see, it's also what keeps your lights on. No, really. It's the same exact idea that connects a massive power plant lighting up a city, the turbocharger that gives a car that extra kick, and even the simple pump bringing water to your house. It is all connected by one brilliant fundamental concept. All right, so what do we call this incredible technology that's behind all these things? Well, it's a turbomachine. Now, let's really break down what that name actually means. At its core, the definition is actually super simple. A turbomachine is just a device that moves energy between a spinning part, we call that a rotor, and a fluid. And that fluid? It could be anything that flows. Air, water, steam, you name it. It's all about that dance between the spinning blades and whatever they're moving. That is the entire magic trick right there. So every single turbomachine you'll ever see has one of two basic personalities. It either produces power or it absorbs it. Think of it this way. On the one hand, you've got a turbine. It takes energy from a fluid, like high-pressure steam hitting some blades, and turns it into work. On the other hand, you've got a pump or a compressor. It does the total opposite. It uses work to pump energy into a fluid, cranking up its pressure or speed. This whole two-way energy thing is so crucial, it really deserves a closer look. So let's call it a tale of two flows. Honestly, the easiest way to wrap your head around this is to just picture a two-way street, but for energy. The energy can either travel from the fluid to the machine, or it can go the other way, from the machine into the fluid. That's it. And this diagram shows that two-way street perfectly. See, on the left, you've got the power-producing side. High-energy fluid comes in, hits a rotor, makes it do work, and the fluid leaves with less energy. Then on the right, it's power-absorbing. We put work in to spin something, which then energizes a low-energy fluid. It's the same core idea, just running in reverse. Okay, so this one simple two-way principle gives birth to this massive, sprawling family tree of different machines. Getting to know this family, from tiny little dental drills to absolutely massive hydroelectric dams, is our next step. So you might be wondering, with all these different applications, how on earth do engineers even begin to classify them all or know which one to use? It looks super complicated, but it's actually pretty straightforward. Turns out you just have to ask three simple questions. First, what's the energy doing? Is it producing power, like a turbine, or is it absorbing power, like a pump? Second, what's it working with? Is the fluid a gas, like in a jet engine, steam in a power plant, or water in a dam? And finally, this is a big one, which way is the fluid actually flowing through the machine? And that third question about the flow path is so key. Just look at these diagrams. In the middle, you've got axial flow. The fluid goes straight through. Great for moving a lot of stuff. Then, on the left, you have radial flow, where the fluid comes in the middle and gets slung outwards at a 90-degree angle. That's perfect for creating high pressure. And, of course, on the right, mixed flow is just a hybrid of the two. Different paths for different jobs. Let's look a little closer at axial flow. See how the fluid moves parallel to the main shaft? It comes in and goes out along basically the same line. It's like a straight shot right through the rotor blades. And this design is incredibly efficient for moving huge volumes of fluid, which is exactly what a jet engine needs to do. And here's its counterpart, radial, or as it's often called, centrifugal flow. The fluid comes in right at the center, at the eye of the impeller, and then it gets thrown outwards by centrifugal force. This design is fantastic at jacking up the pressure, which makes it perfect for things like water pumps and, yep, the turbocharger in your car. Okay, so now that we have the building blocks, let's connect it all back and see just how deeply these machines are built into the world all around us. I mean, the applications are literally everywhere. Our power generation is almost completely dominated by steam, gas, and hydro turbines. In transportation, you can't miss jet engines and turbochargers. And in our daily lives, it's the compressors in our air conditioners and refrigerators, and the pumps that handle our water supply. They are truly the hidden workhorses of our world. And making them even a little more efficient is a massive key to a sustainable future. You know, there's a great quote that really hits the nail on the head. It says, "The most common, practical use for the science of fluid mechanics is designing these very machines." And that's the big takeaway here. Understanding how fluids move isn't just some abstract science, it's the nuts and bolts foundation for the technology that makes our modern lives possible. So, from shooting us across the globe to lighting up our homes, turbo machines were, you could argue, the defining engine of the 20th century. The final question I want to leave you with is this. As we face all these new challenges in energy and sustainability, what new frontiers will these incredible devices help us conquer in the 21st century?